Hi everyone, and welcome to today's Chemistry Daily Booster. This is number 14 in our Paper 2 series, and it is advanced information listed for both the foundation chemistry and higher tier chemistry. What we're going to be doing then is having a look at the Harbour process in more detail. We've mentioned the Harbour process in a previous booster, talking about this is how we make the ammonia that we need for a range of fertilisers. But what we're going to do today is dig down in a little bit more depth to understand what we're doing in this process, what conditions we use and why. So first of all, this little picture should be quite familiar to us. I showed it to us in a previous booster as well. What we have then, we've got our hydrogen and our nitrogen, the two raw materials that go into our reactor vessel. The pressure is increased to a value of 200 atmospheres. Those two gases under high pressure are then pumped into the main reaction vessel here, which is at a temperature of 450 degrees Celsius, and it passes over these beds of the iron catalyst. Once it goes through there, it's going to undergo the reaction and form the ammonia. It travels down into this next little section where we've got water that flows through, which cools it down, and therefore the ammonia will condense to a liquid, and then it collects in this tank at the bottom where we can run it off. Any of the unreacted gases are then pumped straight back into the main reaction vessel. Through doing this and using those three conditions, 450 degrees Celsius, 200 atmospheres and an iron catalyst, we end up with a yield of about 30%. What we're going to do then is we're going to go through the actual conditions we choose and why in turn. First one is going to be temperature. If we consider the actual reaction that takes place in the Harbour process, it's a reversible reaction, therefore we need to know what direction is exothermic, what direction is endothermic. In this case, the forward reaction is exothermic, the backwards reaction is endothermic. If we think back to a previous booster, what we said was increasing the temperature in a reversible reaction is going to move the equilibrium position in the direction of the endothermic reaction. So if we increase the temperature in the Harbour process, we move the equilibrium position to the left, therefore decreasing the yield of ammonia. That's not great, obviously. You might be thinking, okay, so why do we use 450 degrees Celsius then? Why don't we use a much lower temperature? Well, if we lower the temperature, we're reducing the rate of reaction. So what that means is we need to pick a compromise between a high enough temperature to generate a fast rate of reaction, but a low enough temperature to not completely destroy the yield we get. If we look at the little graph on the left here, we can see that there are 4 lines and they're labelled with the different temperatures there. So 200, 300, 400, 500. X-axis is the pressure, Y-axis the yield. What we can see first of all is if we look at the 500 degrees Celsius line, the bottom one, that has the lowest yield of them all. No matter what the pressure is, always the lowest yield. Whereas the 200 degrees Celsius line, always the highest. They can give us a graph like this and ask us to explain what it shows. So here we just need to talk about the fact that increasing the temperature decreases the yield, and then we'd explain it using our ideas about equilibrium position. Second factor, the pressure. Why do we pick 200 atmospheres? At the top we've got our balanced symbol equation for this reaction. So on the left hand side we have 4 moles of gas, 3 hydrogen, 1 nitrogen. On the right, 2 moles of gas. Therefore, if we increase the pressure, the equilibrium position is going to move to the right because that's where the fewer moles of gas are. So by increasing the pressure, we increase the yield. We don't pick a really high pressure for the simple fact that if we are increasing the pressure a lot, then we're going to have quite high costs associated, due to obviously having to generate that high pressure, machinery to withstand the high pressure, and it also becomes a safety risk because any faults in that system would lead to potentially explosive situations, and that's not a good thing. So we use 200 atmospheres as the compromise. The last thing is we talked about the fact that we recycle the gases. Now, the whole purpose behind that is just to reduce wastage. If we were only generating 30% yield and then just disposing of any unreacted gases, that's going to drive up the cost of this process because you'll have to keep getting new raw materials in. Whereas if we recycle those gases, then what that means is we're not wasting any of those raw materials because we're just feeding them straight back into the reaction vessel so they can react to make the ammonia. If there are any bits from today's booster you'd like to go over in more detail, then you do have the videos on the main channel that you can use. You hopefully have access to a revision guide, and of course do have a look at some of the past exam questions around this topic to give you a bit of a feel for the kind of thing they ask. And then don't forget to join us once more tomorrow for our next Daily Booster.